So I think we can welcome Andrew back for round two. Is this Gabs?
Yeah.
Yeah. All right. For Gabs.
Wait. Okay. So in my previous talk, I talked about quantum symbolics, which is kind of an attempt to abstract away a lot of specific details within different Julia quantum libraries. For this talk, I'm going to talk about a specific backend that I called Gabs. So I started Gabs a little less than a year ago, but I made pretty good progress, and I'm getting some contributors to develop some things, and I can help out with review and stuff like that. So I'm happy to present it today. So Gabs is a Gaussian quantum information simulator. So it can basically simulate this large class of continuous variable quantum information, which are Gaussian states and Gaussian operations. You can kind of think of them in analog to the stabilizer formalism, but there are some differences. So with the Gaussian quantum information formalism, you can't do error correction on Gaussian noise with Gaussian operations. There was a really irritating no-go theorem that was published a few decades ago about that. You also can't do entanglement distillation with Gaussian operations. But there are a lot of really neat things that you can do in terms of quantum networking. So you can do quantum teleportation with Gaussian states and entanglement swapping and stuff like that. I don't really want to talk about myself again like I did in the first talk, but I'm with NYU and the Flatiron Institute. I'm interested in tensor networks. Gabs is, it started out as a backend package for the NSF's quantum networking simulator, where we want to sort of have a bunch of different backend classical algorithms for simulating quantum networks. So Gabs is a really nice way of doing that because continuous variable quantum information is everywhere in the quantum networking field. Yeah, just to advertise this again. So Stefan's running a mini grant Symbug Bounties program to help out young developers and get them involved in quantum information. Okay, so when you learn about quantum computing or quantum information in like an intro to quantum mechanics course or quantum information course, you learn about everything in terms of the Schrodinger picture. So you learn about your density matrices and Hamiltonian operators that scale exponentially with the size of your quantum system. And there's, in the continuous variable quantum regime, there is an equivalent representation, and it's called the phase space representation, where you represent your density matrix as this Wigner function that's a continuous variable, and it's written in terms of your quantum harmonic oscillator quadratures. So you can kind of think of them as position and momentum operators on your quantum system. And then you also can map your Hamiltonian operator to a continuous variable function as well. It's called its Weyl symbol. The Wigner function is really interesting. So it's considered a quasi-probability distribution. So it can take on negative values, and a lot of quantum information scientists use that Wigner negativity as sort of a quantum resource because so you can think of like cat states, which we saw earlier in the Piccolo talk, or GKP states. They all possess some sort of Wigner negativity if you look at them in the phase space. But the problem with this is that to introduce that Wigner negativity, you need to inject some sort of nonlinearity in your Hamiltonian that describes like the evolution of your quantum system. And those nonlinearities are really challenging to resolve, right? Because you can get really, really fine quantum interference effects. And also with those nonlinearities, there's a ton of squeezing, which is also really challenging to resolve as well, especially if it squeezes out of your sort of phase space picture. So there's no free lunch there. And it's not really a workaround, but you can still describe like a large class of these states just in terms of their lowest order statistical moments. So what I mean by that is you take your quadrature operators of your multi-mode quantum harmonic oscillator system, and you characterize them in terms of like their expectation values and variances. So these are your low order statistical moments, right? So you have a mean vector for a multi-mode system, and then you have a covariance matrix. And importantly, that scales like n squared rather than your really bad 2 to the n. So you can imagine, you can describe hundreds or maybe even 1,000 quantum harmonic oscillator modes as long as you're evolving them under some sort of transformation that preserves that Gaussian character. So that transformation is called a Gaussian operation. So there's unitary transformations that in the phase space resemble symplectic operations. So you might have heard of that from your classical mechanics course, maybe. But you can also have bosonic channels that are Gaussian and also do measurements like homodyne measurement, or you can even make those homodyne measurements noisy and make them and generalize them to heterodyne or generalodyne measurements. And just to give some examples of these different states and operations, so Gaussian states, there's coherent states, there's bosonic thermal states, there's single mode and two mode squeeze states, and then some Gaussian unitaries are like squeezing and displacement operations and phase shift and beam splitter operations. So that's kind of the regime in which Gabs works in. So we have some important types. So we have like Gaussian state and Gaussian unitary types, which kind of makes sense. And really, they're just wrappers around different Julia arrays. And the only thing that you sort of need to keep track of is sort of the symplectic basis of your multimode system. So really what that just kind of entails is like how you sort of order your phase space variables. Like maybe you can order them pairwise, like I'm doing here with this quad pair basis type, and here the 2 corresponds to like 2 modes in your quantum harmonic oscillator system. You can also do like blockwise ordering, and in the future I want to do symplectic bases for like creation and annihilation operators as well, although there's some problems there with asymmetry. I implemented this detail because in sort of the continuous variable quantum information literature, there's not really like a nice convention in which you like order these things. So it's really easy to encounter bugs if you don't keep track of your symplectic basis. So that's just kind of a detail, but it's, if you don't really care about it at all, you can just kind of pick a basis, and then as long as you define like the number of modes in your quantum harmonic oscillator system, you're fine. Do I want to say yes? Okay. I don't have extreme benchmarks to different packages. One, because there's not a Gaussian quantum information package in Julia, and I haven't done any benchmarks with Python's Penny Lane. But just to give a taste of how powerful just this efficient simulation framework is, here I created a random unitary Gaussian operator, and I applied it on 1,000 Gaussian state, or 1,000 mode Gaussian state, and it happens in 1/10 of a second. So that's pretty powerful. You could never do something like that with a state vector formalism or like even tensor network methods. And because this framework relies so much on just linear algebra operations, I wanted to make sure that you could just pass any sort of array that you want into your Gaussian states and operations. So here I'm importing in static arrays, which is a nice package in which you can do really efficient computations with small matrices and vectors. And here I just pass in SArray into this random state function, and then it creates a Gaussian state wrapped around some a static mean vector and static covariance matrix. And it turns out like for any predefined function in Gabs that creates some sort of Gaussian state or operation, you can pass in this any custom array type you want, and it'll support that. And that includes also like doing operations between these different objects as well. It'll preserve that custom array type. Okay, so let's get into the symplectic analysis. I talked about it earlier, but I'd like to go into a bit more detail since I've done a lot of work with this. So a Gaussian unitary, you can think about it, like I said, in terms of a symplectic operation on your phase space Wigner distribution. And when I was developing this package, I was kind of hard coding all these symplectic operations, and then I realized like there's no Julia package for handling symplectic matrices, and I couldn't find anything else in like Python or C++. So I made a symplectic matrix package. So just to define a symplectic matrix in case you've never heard of it. So there's this thing called a symplectic form, which is this the matrix that I actually expressed, and it's like a non-invertible skew symmetric matrix, and a symplectic matrix is basically one that preserves the congruence of that symplectic form. So the reason why this is so important in like Gaussian quantum information is that this preserves like the canonical commutation relation if you have like a bunch of quantum harmonic oscillator modes. So in symplectic matrices, I basically defined all of these custom array types. So here I have a symplectic array type, which keeps track of the symplectic form because it can take a lot of different variations, and then you can create a bunch of symplectic matrices. You can also, and I think this is the key feature about the package, is that I put in a ton of support, and it's all Julia hard-coded for doing a bunch of fancy symplectic decompositions on symplectic matrices. So just to give an example, so there's a decomposition called the block Messiah decomposition. It's also known as the Euler decomposition, where you can basically factorize a symplectic matrix in terms of an orthogonal symplectic matrix times diagonal matrix with its so-called symplectic eigenvalues times an orthogonal symplectic matrix. And what I really tried doing was like strictly matching like the linear algebra standard lib interface within Julia, and also like custom array types so that these operations are as efficient as possible. And I hope to soon, move this over to like the Julia linear algebra organization so that they can have like full control over it, so I don't have to deal with it as much. But there's other symplectic decompositions as well. So there's like a polar decomposition where you factorize it. It's like a symplectic version of the polar decomposition. There's a Williamson decomposition, Takagi, and I hope to include more soon. But the reason why I'm bringing this all up is that these symplectic decompositions, they actually have like a ton of physical meaning. So going back to that block Messiah decomposition, if I take like some arbitrary Gaussian unitary circuit, I can decompose that into these orthogonal symplectic matrices times like these individual squeezers. And really what this corresponds to physically is like I'm decomposing this, say, a photonic circuit into like passive operations, which correspond to orthogonal symplectic matrices, and then these squeezing operations that are like a diagonal matrix of all your symplectic eigenvalues. Another example is the Williamson decomposition. So if you have a covariance matrix that describes an arbitrary Gaussian state, you can factorize it into a symplectic operation times a squeeze state that's like squeezed along one quadrature axis times the transpose of another symplectic operation. So there's all these like cool little features that you can do, and I don't think they're really there in Penny Lane as far as I know. So that's one feature that I guess distinguishes Gabs from a team of software engineers working on this problem. I guess to talk about another feature, you can do symbolic computation. So I talked about this earlier in the talk, but I'll discuss it again, where you can kind of set up these symbolic quantum expressions and then convert them to your numerical backend of choice. Of choice meaning the backend supported in this package called quantum symbolics. And Gabs is supported with quantum symbolics. So here I'm taking a symbolic expression of a squeeze state times a single mode vacuum state, and then I can express it over and translate it over to Gabs. Or if I want to translate it over to a state vector formalism, I can do that as well. And what I hope to do in the future is have some nice examples of like interoperability between like Gabs and Quantum Toolbox and Gabs and quantum optics, because there's definitely some optimizations that can be done there if you just transfer over to this phase-space formalism for certain subsets of your problem. And then another thing that just kind of worked out of the box, and I think it's like a great example of Julia's multiple dispatch feature, is I was using symbolics, but rather than creating like an entire symbolic representation of like a quantum state or a quantum operator, I had Gabs basically wrap around like symbolic variables contained in my mean vector and covariance matrices, and it just like worked very, very beautifully out of the box. So this could be really cool if you're just trying to get like analytical um, expressions of like elements within your covariance matrices and mean vectors. So like here, I defined these symbolic variables. It's in purple from the symbolics package. And then I defined a coherent state. And then I defined like a fiber attenuator bosonic channel with these symbolic variables. And what happened was, even if you just do some channel application onto the state, it still preserves those symbolic elements. And then you have a quantum state that has even more complicated covariance matrices and mean vectors. So it's kind of an interesting feature, and we've heavily tested it, and it works throughout all of our different methods in the package. I wish it would work for symplectic decompositions, but it's rather challenging to do like symbolic factorizations and stuff like that, especially for like many mode quantum systems. There's this theorem called the Abel-Ruffini theorem that basically prevents you from doing like these sort of symplectic decompositions for like more than 4 modes. But yeah, and as I talked about before in the quantum symbolics package, so Gabs is part of quantum interface, which is basically a package meant to have different inner workings between sort of these backend Julia packages. So maybe you can have conversions from quantum optics to Gabs, or, you know, convert directly from a symbolic representation to a numerical representation. And that kind of stuff can go all under the hood of Quantum Savory, which is this networking simulator that sort of abstracts away all of those things. Okay. So there's, even though this Gaussian character is very classically simulable, it doesn't work for a lot of states and operations that we really care about in continuous variable quantum information. So that being said, you can simulate linear combinations of Gaussian states. And the only thing that you really have to care about is like, okay, all the Gaussian states in my non-Gaussian superposition, as well as the coefficients in front of all of them. So this was implemented by a master's student at UMass Amherst. And basically, we created this framework in which you can take arbitrary superpositions of Gaussian states and see how it works, like see how fast you can get it. So here, I created this. I didn't show the code for this, but I created this cat state just with the Gaussian framework, because you can compute observables like your Wigner function, or you know, you can compute fidelity between different non-Gaussian states, just invoking the linearity of this non-Gaussian superposition. I was inspired by Aaron's 3-legged cat state in his Piccolo presentation earlier today. So I decided to just put up a slide where you can quickly make it with Mach-E. But you know, you can plot any Gaussian state you want with Mach-E with Gabs. I just thought this was a fun.
Is credit.
Oh yeah, it's quantum. So yeah, I guess future directions. Right now, we're working on implementing GPU support. I think this will be really helpful with this linear combinations of Gaussian states, and like dealing with all of the memory there. And you can do some parallel optimizations as well. We're working right now in developing the express functionality, which we typically use for quantum symbolics, and basically just using express to translate numerical representation of a Gaussian state in Gabs to a numerical representation, say in Quantum Toolbox or quantum optics, because I think that is like a really nice way of going back and forth between the two different frameworks. And since I do tensor network stuff now, like I'm really interested in delving more into this non-Gaussian regime with tensor networks, maybe just like a simple matrix product state representation of your Gaussian states. I think that would be pretty straightforward to do. And then there's a really interesting problem in continuous variable physics, which is called Gaussian boson sampling, and you can do this for like relatively small quantum systems, and I think that'd be interesting to simulate and of use to some people. So with that, thanks for your attention.
Any questions?
Yeah, first off, this is all super cool stuff, and it's been so long since I thought about symplectic geometry, and I never thought I'd come back to it.
It's cool stuff.
Yeah, it's super cool. I have to go reopen that book. So I'm curious about like mapping Hamiltonian evolution into these spaces. Like if I want to do that, like is that possible, basically?
Yes, as long as the Hamiltonian evolution corresponds to a symplectic operation in phase space. I don't really understand like what you're.
Okay. We talk about this after. I want to control in this. I want to basically control these things in this representation, because this seems like a very nice representation. But like, if I have a Kerr-Cat Hamiltonian, like these terms in it, with control terms in them, like, would I be able to map that into like some representation that would be able to act on this n squared representation of the Gaussian state if I wanted to like constrain it to remain Gaussian?
No, not a Kerr-Cat representation. I mean that because there's nonlinear terms, right?
Yeah, okay.
And you can't simulate nonlinear.
But without nonlinear terms, you could.
Yeah, absolutely.
Okay.
Yeah, but I'm very interested in sort of those slightly non-Gaussian Hamiltonians like Kerr, Gates, and quartic Hamiltonians as well, because I think there's definitely low-hanging fruit in representing them with like matrix product states, I would say. Yeah.
Cool.
Do you think it's possible to compress further the Gaussian states? As I understand, you can represent the Gaussian state because they're simple in some way. And do you think the representation you have of them is optimal, or can you use more using the structure of the symplectic group itself? Do you think that's possible?
I didn't hear the first part of the question.
As I understand, you make use of the fact the symplectic states are simple in some way, therefore you can efficiently store them because they have simple structure. And my question is, do you think you're optimal in your storage of these states, or would it be possible to be even more compact using the structure of the symplectic group?
I don't think you can make it any more compact with this Gaussian state formalism. Obviously, I'd be very interested in using that the symplectic structure for like matrix product state representations and seeing if there's some interesting decompositions you can do there. But I think for Gaussian states, it's as compact as you can get.
I don't understand how you managed to describe the cat state as a sum of Gaussian state within your framework. How do you do that?
Internal details, I define a Gaussian linear combination type, and then I have the coefficients stored in a vector, and then my Gaussian states. So when I compute like a Wigner function, I'm just, computing products of the Wigner functions of each term in my linear combination.
Okay, so you can describe a very large total number of a cat state very efficiently with this.
Nice. It's pretty efficient too. Like I quickly timed this plot, and it took like 100 milliseconds or something.
Nice.
Yeah.
How fleshed out is this low rank representation capability of superposition of coherent states? In particular, do you have support for representing operations as some Gaussian channels? That's frequently done for stabilizer states. You represent your operation as a sum, as a channel, as a sum over, say, poly operations, and you have some rule for how your superposition of stabilizer states grows. And sure, it becomes more and more expensive, but it's neat. Can you do something here as well to have operations defined in this formalism as well?
I have not. I think it'd be really interesting. Yeah, I don't. But I mean, you can apply any Gaussian operation on these superpositions because it's pretty easy to do. You're just applying them one after the other.
Yeah, I'm thinking more about...
Yeah, I know. No, I haven't. I don't know how hard that would be. Probably not too hard, but...
Well, there's a hackathon on Saturday.
yeah.
Any more questions? Okay. Let's thank speakers again.